GCE Advanced Level Chemistry Practical Series Experiment number 43, Preparation of Biodiesel. In this experiment, we aim to provide you with the necessary knowledge on how we can prepare an environmentally friendly liquid fuel source, which is biodiesel, and we are going to try and understand the advantages that come along with the use of biodiesel. Now, let's move on to identifying the equipments and the reagents we will be using for this experiment. Students, to conduct this experiment, we will be needing the equipment and the reagents we have here. Starting with the reagents, we will be using vegetable oil, sodium hydroxide pellets, methanol, Erlenmeyer flask, 250 milliliter Erlenmeyer flask. We'll be using beakers, measuring cylinders. Apart from that, to measure the temperature, we'll be using a thermometer. To measure the mass of sodium hydroxide we need, we'll be using watch glasses and spatula. We'll be using a separation funnel, or we call it a separating funnel as well. So this funnel is used to separate out the two layers that are formed towards the end of this reaction. The product biodiesel that is formed is not going to be soluble in the aqueous layer, and we are capable of separating out the two layers with the use of a separation funnel. And then we have our digital balance, which we will be using to measure the mass of sodium hydroxide that is needed. We have a heating setup here. We will be using a tripod with a speed burner. So we will be using this setup to heat up the reaction mixture. And then we have a retort stand with a holder for our separation funnel. So when we are separating the two layers, we will be using this setup to hold the separating funnel. Now, we have identified the equipment and the reagents we need for this experiment. So all that is left for us to do is moving on to actually conducting the experiment. Let's move on and start our experiment. Students, now we are going to be producing biodiesel here. So before we start producing biodiesel, let's learn a little bit about biodiesel. So biodiesel is going to be produced with the use of a renewable source, which is plant oils. We will specifically be using non-volatile plant oils here. And when you take plant oils, students, you have triglycerides in the plant oils, and apart from the triglycerides, you will have free fatty acids. So this is a very important point here, so you have to keep this in mind. Plant oil usually has triglycerides along with a certain amount of free fatty acids. Now, a triglyceride is consisting of a glycerol molecule forming ester bonds with long chain fatty acids. So when it comes to triglycerides, we have 3 ester linkages or 3 long chain fatty acids forming ester bonds with the triglyceride or with the glycerol molecule. So when we are trying to form biodiesel, all that we are doing is we are changing this ester or the triglyceride that we have into a different type of ester. We say we are trying to form methyl esters. So when you are trying to do that, we will be using sodium hydroxide as a catalyst. And this process of converting triglycerides into fatty acid methyl esters is referred to as a trans-esterification process. This is a type of a reaction that is referred to as a trans-esterification process. So when you are doing this, we use sodium hydroxide as a catalyst. So if you have free fatty acids in the ester, sodium hydroxide can react with these free fatty acids and can form sodium salts of the carboxylic acid. So if you consider the free fatty acid to be an RCOOH compound, after reacting with sodium hydroxide, it will get converted into RCOONA, which is actually soap. So students, this particular reaction that may take place would lead to the reduction in the catalyst sodium hydroxide and might hinder the process of manufacturing biodiesel. So the oil that you take, in this case the vegetable oil that you take, should have a very low amount of free fatty acids. To be exact, you have to make sure you have less than 2% of free fatty acid by mass. Or in other words, you can say the acid value of the oil should be less than 0.1 milligrams of potassium hydroxide per gram of oil. So what is this acid value? Acid value is the amount of potassium hydroxide that is needed in milligrams to neutralize the free fatty acid content in 1 gram of oil. So if you take 1 gram of oil, there will be certain amount of free fatty acids. These free fatty acids can be neutralized by the addition of potassium hydroxide. So the mass of potassium hydroxide needed to neutralize the free fatty acid in 1 gram of oil should be less than 0.1 milligrams. So this is the understanding you should have going into the production of biodiesel. However, students, when it comes to industrially manufacturing biodiesel, there are about 5 steps. First step being treating the oil, removing all impurities from the oil and saponifiable and non-saponifiable components and pigments from the plant oil. And then secondly, we can move on to preparing our catalytic mixture, the mixture of sodium hydroxide and methanol. And thirdly, we can mix the vegetable oil with the catalytic mixture and allow the reaction to take place. At this point, there will be 2 layers formed. And the fourth step would be separating these 2 layers. And fifth step is further purification of our biodiesel layer by sending water and dissolving out all the glycerol that is formed. And when it comes to purification, you have to remove methanol also that is present in biodiesel. If you use excess methanol, that is going to be present in the biodiesel as well. So through heating, you can remove methanol as well. So these 5 steps are usually seen when you are preparing biodiesel industrially. In this experiment, we are going to follow only a few steps to observe how biodiesel can be prepared in a lab setup such as this one. So now let's first move on to measuring sodium hydroxide that we need and start our practical. Now we will take our watch glass, and before placing the watch glass on our digital balance, we turned it on. So we will place the watch glass on our digital balance like so, and we can remove the mass of the watch glass from the digital balance reading by tearing the balance. So we have pressed the tear button. Now we have removed the mass of the watch glass from the digital balance reading. Then we have here sodium hydroxide. So in this container, we have sodium hydroxide in the pellet form. We will take a small amount of sodium hydroxide and place it on our watch glass here. Keep in mind, students, they only need you to use 0.5 grams of sodium hydroxide. We have 0.49 grams of sodium hydroxide. Now students, we have measured 0.49 grams of sodium hydroxide. If I had added one more pellet, it would have gone well above 0.5. So to avoid doing that, we will use 0.49 grams of sodium hydroxide here. And then we will transfer this into our Erlenmeyer flask. We will no longer need the balance. We can remove it as well. So in this Erlenmeyer flask, we have our sodium hydroxide, and we are going to dissolve it not with the use of water. We are going to dissolve it with the use of methanol. So we have our methanol here. We can use about 20 milliliters of methanol to try and dissolve this sodium hydroxide. So we have a measuring cylinder. Let's take about 20 milliliters. Of methanol. So we have taken about 20 milliliters of methanol, and we are going to try and dissolve the sodium hydroxide in this methanol. And keep in mind, students, this is what we do when we are preparing our catalytic, where we have our sodium hydroxide dissolved in methanol. So let's take our methanol, add a small amount of methanol, and let's try and dissolve the sodium hydroxide. By stirring it, you will be able to dissolve the sodium hydroxide that we have here. We'll add the whole of 20 milliliters of methanol into the Erlenmeyer flask, and we can continuously stir until the sodium hydroxide that we have here completely dissolves. Alternatively, we can use a stirring rod as well. Or we can stir the contents in the Erlenmeyer flask by swirling the Erlenmeyer flask around. You might observe little by little the sodium hydroxide starts to dissolve. Now we will completely dissolve this and keep it prepared for the next step in this experiment. Now students, we have dissolved our sodium hydroxide in methanol. It is important to note that we didn't use water to dissolve sodium hydroxide. We used methanol to dissolve the sodium hydroxide we measured into this Erlenmeyer flask. It might take a while when you are conducting the experiment to dissolve sodium hydroxide in methanol, but if you are patient enough, it will get dissolved after some time. After that, we are now moving on to taking some vegetable oil into 250 milliliter beaker, and we are going to heat it to 40 degrees Celsius. So to measure the amount of vegetable oil we need, we will be using a measuring cylinder, and we have our vegetable oil here. Students, as I mentioned before as well, the first step when it comes to preparing a biodiesel is to treat the vegetable oil or the plant oil that you're using before using it for this particular reaction. So usually the plant oils that we obtain will have a lot of other material than just the oils we need. such as different types of pigments and sometimes solid particles and free fatty acids, other non-saponifiable compounds will be there. To remove these compounds, you can actually send the oil through activated fuller earth at 90 degrees Celsius. So when you send it, majority of these compounds will get removed from the oil, and you can use the resultant product to carry out an experiment like this. So we have our vegetable oil here. We will measure 100 milliliters of our vegetable oil. We have taken a little bit extra. Now students, we have measured 100 milliliters of the vegetable oil that we are going to be using for this experiment. Let's transfer this amount of vegetable oil into our beaker here. It will take some time for all of the oil to be transferred into our beaker. After transferring all of our vegetable oil into our beaker, we are now going to heat this vegetable oil until it reaches a temperature of around 40 degrees Celsius. And at that point, we are going to add the vegetable oil to our catalyst mixture that we prepared earlier, and the entire reaction mixture is going to be kept between a temperature of 50 to 60 degrees Celsius. So let's place this vegetable oil on our tripod here like so, and let's start heating it until it reaches a temperature of 40 degrees Celsius. We can use a thermometer to measure the temperature that it is currently at. Currently, it is at a temperature of 32 degrees Celsius. Now students, we have heated this oil to 40 degrees Celsius. So we have turned off our spirit burner, and the temperature at this point is 40 degrees Celsius. Now, since we have measured the temperature, we can remove our thermometer and we can move on to adding this oil into our catalyst mixture that we have in front of us. So we prepare this catalyst mixture by adding sodium hydroxide and methanol together. Now we will be adding the oil that we heated up into our sodium hydroxide and methanol mixture. And after adding these two together, we have to continuously stir until two very clear layers form. And students, to speed up this reaction, we can heat this mixture up to a temperature between 50 to 60 degrees Celsius. So let's light up our spirit burner once more, and we'll heat this mixture. And if it gets too hot, we will remove this mixture from the setup And again, after it cools down, we will heat it again until we can see very clearly two layers being formed. Let's measure the temperature of this mixture. The temperature of this mixture is somewhat above 50 degrees Celsius. Now students, keep in mind to take the Lidmeyer flask off of the heat every once in a while, because we need the temperature to be maintained between 50 to 60 degrees Celsius. After the system reaches 50 degrees Celsius, you do not need to keep it for a long time on the heat. So you can remove it and continue to stir off of the heat. So when you are stirring, what you're trying to do is making sure the two layers, which is the oil layer and the alcohol layer, mix really well, as these two layers are usually not very miscible. So to facilitate the reaction, we have to continuously stir until we see the formation of two layers form again. So when you see the formation of two very distinct layers, then we can be certain that the biodiesel has been produced. Students, now we have been stirring this mixture for a while. To make sure the reaction happens efficiently, we have to keep stirring until two layers start to appear again. So you can see here in this reaction mixture, there is formation of two layers again. And the above layer is our biodiesel layer. And at the bottom, we have our sodium hydroxide, methanol, and glycerol layer. So right now, what you see here is the formation of two layers. So right now, what you see here is the formation of two layers when you are carrying out this reaction. So we can continue to further mix this to make sure if there are any other excess amount of triglycerides and the catalyst mixture that still can react to one another present in this mixture. To facilitate them reacting, we can continue to stir it for a while, and after that we are going to very clearly observe the two layers formed and then transfer this mixture to a separation funnel or separatory funnel, and then we will separate out the top layer. We will again observe the formation of two layers after mixing it for a while. Now students, we have mixed this reaction mixture and we have allowed it to settle for a while so that we can observe the two layers very clearly, because it takes a while for this layer separation to happen. Now if you observe here, we can see two layers here, and on the above layer is where we will find our biodiesel. Biodiesel is a mixture of fatty acid methyl esters. So we have different types of fatty acids undergoing trans esterification reaction, and forming fatty acid methyl esters, which is normally abbreviated to FAME. So in this fatty acid methyl ester mix that we have here as the biodiesel, we have different types of carboxylic acids such as lauric or myristic, palmitic, and stearic acids. So these types of different acids will undergo transesterification process and form fatty acid methyl esters, and this mix of fatty acid methyl esters will have different number of carbon atoms, or different types of methyl esters are present here. Majority of the methyl esters will have a carbon atom number ranging from around 12 carbon atoms all the way up to 18 carbon atoms. The biodiesel we have here is going to contain fatty acid methyl ester mix, which will have a different number of carbon atoms ranging from 12 carbons all the way up to 18 carbons. And apart from the biodiesel we have here on the top layer can also contain small amounts of unreacted triglycerides, or diglycerides can be there. Apart from that, small quantities of glycerol also might be present in the top layer, which is the layer that contains mainly biodiesel. And on the bottom layer, you are going to have mainly glycerol, unreacted or excess methanol that we used along with the catalyst. So on the bottom layer here, those are the main compounds that you can find, mainly glycerol, unreacted or excess methanol that we added, and sodium hydroxide will be found on the bottom layer. So now we can move on to transferring this mixture, or two layers rather, into our separating or separatory funnel. So we have our separatory funnel or separation funnel. We can make sure the tap is all the way closed, and then transfer our two layers of biodiesel and glycerol into our separatory funnel. So I've made sure that this tap is fully closed. Now all that is left for us to do is transfer these two layers onto our separatory funnel and then separate out the two layers. So we will bring this setup over here, and we can now remove this lid and transfer our biodiesel and glycerol layers. We will do it very slowly. So when you're transferring these two layers, we have to be very slow about it without causing much agitation. We have to transfer it into our separatory funnel. When adding these two layers into our separatory funnel here, there could be some agitation that take place. So we will allow this mixture to settle in the separatory funnel for a while before we move on to separating the two layers into two separate beakers. Students, in the previous part of this experiment, we reacted methyl alcohol with sodium hydroxide, and then to that mixture we added vegetable oil, and then we allowed the reaction to take place in this reaction mixture, and later on we saw the formation of two layers, and then we transferred this mixture onto a separation funnel. So in the separatory funnel, we could not very clearly observe the interface between the two layers because these two layers were still settling down, and we couldn't very clearly observe the two layers separately. But now we have allowed the two layers to settle for a while, and we can very clearly observe the two layers that are formed here. And the interface between the two layers is also very clearly visible here. On top, you have your biodiesel layer. As I mentioned earlier, this contains a biodiesel, which is fatty acid methyl esters. So these fatty acid methyl esters might contain a varying number of carbon atoms, ranging from anywhere between 12 to 18 carbon atoms. And apart from that, this top layer also might contain triglycerides that have not reacted, diglycerides, and small quantity of glycerol. However, on the bottom layer, what you mainly find is the glycerol that has separated out from the top layer. You have glycerol here. Apart from that, the excess methanol that we have added to the reaction mixture will also be found along with some sodium hydroxide. So we can very clearly observe the two layers. Now we are going to separate the two layers with the use of our separatory funnel. So we have a beaker here labeled glycerol because this bottom layer that we have here mainly contains glycerol. So we can open the tap and allow the glycerol layer to get collected into our beaker that is labeled glycerol. So as soon as all of the glycerol layer is taken into our beaker here, we can close the tap. At that point, only the top layer will stay or remain in our separatory funnel. And then we can remove that layer into another beaker so that we can obtain our biodiesel separately. So let's open this tap and slowly remove our glycerol into this beaker, and we have labeled it glycerol as well. As soon as this biodiesel glycerol interface comes to where the tap is, we will close the tap, and to a separate beaker we will collect our biodiesel. Now, students, you have to keep in mind, glycerol is a product that is used in many industries, especially the cosmetics industry. Now, as the glycerol biodiesel interface gets close to where the tap is, we will get ready to close this tap, making sure we don't allow any biodiesel to get into our glycerol that we have here. Now, students, we have separated out our bottom layer into a beaker. So what we mainly have here is glycerol. There will be small amounts of excess methanol that we used. Apart from that, a certain amount of sodium hydroxide might also be present here. However, main component that you find in this bottom layer of uh, the two layers was glycerol. So as I mentioned earlier, glycerol is a widely used compound, especially in the cosmetic industry or skincare industry. It is used quite often. So this is a very valuable product for those industries that actually use glycerol. Now, let's move on to collecting our biodiesel layer into a separate beaker. So we have here a beaker labeled biodiesel. So what we have here on the top layer, out of the two layers, is mainly biodiesel. So let's collect our biodiesel into this beaker. And now students, we have separated out our biodiesel layer into a separate beaker. So we have diesel here, we have biodiesel, and the vegetable oil that we used to form our biodiesel. Students, when we were talking about biodiesel, we learned biodiesel is basically a mixture of fatty acid methyl esters. So we have long chain fatty acids that are reacted with methanol to form fatty acid methyl esters. So these long chain fatty acids were originally found in triglycerides. So they had ester bonds with the glycerol molecules forming triglycerides. And when we added sodium hydroxide and methanol mixture to these triglycerides, we saw a trans-esterification took place to form fatty acid methyl esters. So this is a mixture of fatty acid methyl esters that we consider to be our biodiesel. And we have diesel here. Diesel is mainly a mixture of hydrocarbons. So majority of the hydrocarbon molecules that we find in diesel have a varying number of carbon atoms, mainly ranging from somewhere around 10 to 20 carbon atoms in these hydrocarbons. So diesel and biodiesel are two different compounds, but they do have similar properties, such as both of them can be used to make the engine function. Now students, again for comparison, we have vegetable oils to prepare our biodiesel, and we have the biodiesel we prepared, and apart from that we have diesel that is normally used in a diesel engine. So now let's take a small piece of filter paper and we'll dip it in biodiesel and set it on fire to observe how the combustion of biodiesel take place. So we will be using a pair of tongs to hold our filter paper, and we will dip it in the biodiesel, and then we'll move a step back and we will set the filter paper on fire. The reason for moving a step back would be because we are having a few different fuels here, and we wouldn't want anything to catch fire. So as a precaution, we can take a step back and move slightly away from these fuels and conduct this experiment. So let's dip this filter paper in our biodiesel, and we will move a step back and we will set this filter paper soaked in biodiesel on fire. As you can see students, when you set the filter paper soaked in biodiesel on fire, it easily catches fire and burns for a little while longer than a usual filter paper would. So Now, let's move on to another comparison. Now students, we have in front of us vegetable oil, biodiesel and diesel. And in three petri dishes, we have one piece of cotton wool. We are going to dip each of these cotton wool pieces in diesel, biodiesel and vegetable oil separately, and we are going to observe how these cotton wools will burn when we set them on fire. So first, let's take the first cotton wool piece and we'll dip it in vegetable oil. Now, after wiping the tips of the tongues, we will be moving on to the second cotton wool. Now we'll take the second cotton wool piece and we will dip it in our biodiesel. After wiping the tongues, pair of tongues that we're using, we will now pick up the third cotton wool piece and we will dip it in diesel. Now students, before we move on to setting these cotton wool pieces on fire, let's remove these biodiesel, diesel and vegetable oil beakers away from the petri dishes, as diesel and biodiesel may catch fire. We will move them away and we can bring each of these petri dishes here and now set them on fire. Now students, what we have here is a piece of cotton wool dipped in vegetable oil. What we have in the middle is the biodiesel that we formed. And on the left hand corner, what we have here is a cotton wool piece that is dipped in diesel. So now let's set each of them on fire and observe how they burn. Now students, this is our vegetable oil. We have our biodiesel here, and on the left hand corner we have our diesel. So now students, as you can see here, when it comes to the vegetable oil, you don't see a huge flame produced. When it comes to our biodiesel, we can see it is burning considerably well, but not as much as diesel. And when diesel is getting burned, you can see the formation of a black smoke due to the unburned carbon that we see here. When diesel is getting formed, you can see the formation of the black smoke. So we can be certain that we have produced biodiesel. As you can see, the biodiesel is burning way better compared to the vegetable oil that we use to form this biodiesel. Now let's turn these off as we are collecting a lot of smoke in the lab. We will turn off each of these uh, flames that we have here. So this is the biodiesel uh, flame. We will observe it for a little while longer. As you can see, it burns really well for quite some time. A usual cotton wool piece wouldn't burn for this long without a fuel helping it to burn for this long. I hope you have observed the flame that was created with the use of biodiesel. Now we'll go ahead and we'll turn it off. With that, students, we can conclude our experiment. Keep in mind, students, industrially, when you're preparing biodiesel, we have around 5 different steps that I mentioned earlier. You will be pre-treating the oil and purifying it a little bit, and you will be then forming your catalyst mixture. And on the third step, you'll mix the catalyst mixture and your vegetable oil and allow the reaction to happen. In the fourth step, you will separate the two layers, and the bottom layer would contain glycerol and the top layer would contain biodiesel. And after the separation has happened, in the biodiesel layer, we will further purify it and remove the excess methanol that you might find in the biodiesel, and apart from that, there will be small trace amounts of glycerol that you might find. So you can wash the biodiesel with water, and to remove the methanol, you can heat the biodiesel. However, you have to keep in mind, after the preparation of biodiesel, there's usually a purification step. In the lab, when it comes to conducting this experiment, we wanted to observe simply the formation of biodiesel, so we didn't go along with the purification process of biodiesel. So with that in mind, we can conclude our experiment and move on to our more important theory parts and questions revolving around this experiment number 43.